Second up, we have Adam, LaMee, and you can go ahead and share your screen, Adam.
All right, I'll share that in just a second. Thanks everybody for being here. Thanks Renata for having me. Yeah, I'll first say that it is a chaotic world, so I really appreciate everyone taking time out of your life. Maybe this is a little bit of a respite for you to focus on some positive change in the world. If so, anyway, thank you for being here. So my name is Adam LaMee, and I work at the physics department at University of Central Florida down in Orlando. I taught high school physics for 10 years before I came to UCF, and that was 6 years ago. So as part of my role at University of Central Florida, I do some physics outreach and physics teacher recruitment for this project called PhysTech, which is a national initiative to increase the number of qualified high school physics teachers. And so in that, I interact a lot with local school districts because we need to have jobs lined up for our graduates who are looking to go into high school teaching. And we want to have a nice line of communication. And so this great project arose sort of organically from that interaction, is that you know, one of the keys to getting folks to be a good partner for you is to ask them what they need first off, right? Do they have any problems that they're hoping to get some help on? Because I know that I was going to ask them for help on some things. And they said, wow, you know, we're getting all this pressure from the State Department of Education to do more coding instruction and computer science from elementary all the way through high school. And we don't really know how to do that large scale. So that happened serendipitously at the same time that I was working with some folks in high energy physics on using Jupyter as a platform to do some coding and data science instruction. So I'll show you, first and foremost, we decided that there's lots of computer science instruction that's really great, and it's already out there, right? Code.org, CS for All, these are wonderful initiatives, and that wheel didn't need to get reinvented. So since my background is in high school science teaching, we took the approach of, can we take things that we used to use Excel for and Google Sheets and use programming instead? To analyze large data sets or relevant data to whatever the middle school or high school science course curriculum was. So our focus was on teaching science concepts and not on teaching programming. So that means that the bar is pretty low for the programming knowledge that needs to happen. Right, our largest pool of teachers using these were middle school science teachers, and probably 1 out of 200 had programmed before, right? So we needed a really easy on-ramp. So I'll share my screen. Here's the introductory activity that we use. And it's in a Jupyter notebook. We use the, I'll tell you a little bit about the platform that we use in a minute, but the code is already here, and students and teachers initially just learned how to run a little bit of code and do some math, right? Add 2 plus 2, right? 5 minus 4. We'd prompt them to do some work with assigning values to variables and then manipulating those a little bit. And so this activity typically takes about 10 or 15 minutes for a pair of students or a pair of teachers to go through. And there are some questions later on that prompt to, you know, try changing a value and then see how that changes the output. We can see that we get something different. So that's the extent of the programming proficiency that's required for these. But that allows us to then go into activities like this. So this reads in some data from NASA GIS temp. And the code already works error-free, and we try to minimize the number of lines of code that it took to do each task. So that typically these activities will start off reading in some large data set and then previewing the first few entries. So we have years, 1880 up to 1884 with some various temperature readings. And some information on the size and shape of the data set. And then it makes a plot. And the student's task is twofold. First, to figure out what the heck is going on here and what this says, right? And then to edit some of the parameters of the graph to make it more suited for, more descriptive of the data being presented. And so by hunting around in here, they'll see, well, on the x-axis, that's the year column in that data frame. And then on the y-axis, we have January to December, and a little bit of dialogue between a pair of sixth graders, and they're pretty quick to come up with better labels and titles for this. So hunting around, they'll see that it says, I need a label down here on the graph on the x-axis, and up here it says, I need a label prefaced by X label. Right, there are lots of different ways to assign text to an axis, so we try to choose commands and syntax that were easily readable for non-programmers. And they do things like change the axis label and then replot their graph, and now it says year, right? So they would do things like maybe change the ranges on the X or Y axes, change the title or axis titles, and then answer some science questions of what did the data tell us? So we have a set of these activities dealing with life science, earth science, physical science, everything from populations of, here we have in the Florida Everglades, some python and white-tailed deer populations, and you can imagine what that data indicate. Things like earthquake data. The US Geological Survey has this wonderful CSV file that updates every 15 minutes with seismic sensor readings globally. There are thousands of them in this network. And this plots a map of the Earth with a dot for every seismic sensor reading. And it maps out things like plate tectonic boundaries. So this gives us an inquiry-based way to, for students to learn about things like plate tectonics really organically by looking at a data set of where do tremors happen and noticing that it's not randomly distributed across the globe. Anyway, so we have star catalogs, tidal height data that you can tell the difference between a spring tide and a neap tide. It may have been a long time since your 6th grade science. Maybe that was the last time that some of us thought about the difference between spring tides and neap tides. But looking at tidal height measured every 20 minutes across the span of 20 years, you see this nice oscillation with a monthly variation. So, and then some sort of traditional physics topics like position graphs and velocity graphs, and then some particle physics stuff that was supported by some high energy groups that I work with. So my website here that hosts all this is called codingink12.org. Although we're starting to use that at the university level as well at UCF for some undergraduate physics activities. And there's a teacher's page on here, so I won't go through all of the boring details, but if any of this interests you logistically, on the teacher's page, I have some descriptions of the tech choices that we made. So you might recognize that we use Python for all of these, in part because I come from a physics background, and that's pretty ubiquitous where I work, as well as that that's a pretty minimal syntax language. And so for people who don't know how to program anything, that seems to be the easiest on-ramp. We use Jupyter because it has this great feature. For those of you not familiar using Jupyter notebooks, right, that's the interface that you just saw, and that has, you know, you get your rich text formatted, and you can embed hyperlinks and images and videos, as well as your code and the output all in one window, and it runs in a web browser, which we found is really intuitive for absolute novice science students to use. So that introductory activity that I showed you with learning how to do 2 + 2, with zero preparation, we have classes of middle school students working in pairs, and they'll go straight to that. They'll look at it at first and think, okay, I don't know how to program, what is this? And about 5 minutes later, they're doing all kinds of cool stuff. Then, kind of unguided, we can prompt them to go to one of these data science activities. And since the code already works, they're not having to wrestle with tracking down error messages and that sort of thing. And it has worked surprisingly smoothly, despite the audience's lack of programming experience. Now, the last thing that has really made this critical to rolling it out large scale is not requiring local install of Jupyter or Anaconda to run this. We started using Binder, which is a great group that was related to Project Jupyter, where you can serve an interactive Jupyter notebook. But that's not for production use, really. It's great for things like workshops and meetings and conferences. But when we're talking about, 200 middle school science teachers that each have a class of 30 students, and it's got to work the first time, no, 404 errors or anything like that. Google Colab has been our go-to resource. And the neat thing about Google Colaboratory is that it integrates with Google Drive seamlessly. So you can run your Jupyter notebook and then save it to your Google Drive. A lot of schools are using Google already. The downside is that it requires a Google account. And there's all kinds of not only logistical, but ethical issues tied with, let's say, being linked to a third-party corporation that could cancel their service at any time or do things that maybe we think are unsavory. Right, the Google AI has been making the news a lot recently for all of the wrong reasons. But all that being said, Google Colaboratory has allowed us to do this with thousands of students a year with a pretty easy rollout. So I'll give you, here are a couple slides from a talk that I'm giving next week. Just things that we're looking at next. Jupyter Book is a more robust version of Jupyter. And so you can almost have like an interactive textbook, but it's all composed of Jupyter notebooks. So imagine your all of these activities being nicely packaged in a single book, but you can still run this either locally or through some online server. The folks at Jupyter and Binder have now started, just this past year, a nonprofit called 2i2c, looking at Jupyter cloud service options to help get around being beholden to services like Google Colab, or Amazon offered something similar through Azure Notebooks, but they, with sort of short notice, terminated that project this past fall. So if Google did that, we would be dead in the water right now. So 2i2c is something that's worth looking at. And we're also looking at new data sources. You can imagine that for each of these activities, since we're really focused on the science content and not the programming, we're getting more wide-scale adoption by science teachers and school districts with this, namely because teachers don't have to carve out extra time to do these data science activities, right? But instead of the plate tectonics activity that they've done for the last 5 years, they do this one instead. And it takes the same amount of time. They're able to ask students similar levels of questions. And so then it just remains to find an appropriate data set for every bit of science content in a science course. And maybe not every bit, but we have about 5 or 6, for a few different projects, we have about 5 or 6 of these per grade level, spanning 6th, 7th, and 8th grade. And then that was continuing to grow when the pandemic hit. So I'm hoping that we pick that back up. And so CERN, this is the particle physics lab in Switzerland, has a great open data resource. And then the University of California, Irvine machine learning repository is a wonderful place if you're looking for data sets. So I feel like this is really the, what I've been working on is the precursor or the K12 version of what Mandy is looking at, is doing with her undergrads, right? It's a little bit more structured. Here's the data set, tell me what you see, and manipulate some things. And we're hoping that at the high school and at undergrad level, this really primes us for more open-ended, hey, find a data set that you want to investigate and come up with some research question that you think is answerable with that. A couple other things to look next are, more scientific studies of how this stuff works. Right. Anecdotally, we suspect that our students are, these middle school students are learning some computer science and computational thinking and some self-efficacy, like Mandy's polling. But we haven't had the resources to actually probe that stuff, looking at accessibility for different kinds of learners, looking at other research data that I mentioned, expanding into machine learning and AI. We have some stuff with high energy folks at CERN that we're looking at, but I'm always looking to partner with whoever's out there, whoever wants to do something interesting. I'm always game. My default answer is yes to whatever question it is. So I'll close this just by saying that, so we've impacted in the past few years over 15,000 middle school students. And it's at a low level, right? Because this is just a step up from having them use Excel to analyze a data set. But these are students who are at 5 or 6 times throughout the school year interacting with Python and Jupyter and asking some really interesting questions of large data sets that we can't really wrap our heads around just by looking at the screen. And we've done it on a ridiculously shoestring budget. These activities were developed for a couple years, and our local school district, Orange County Schools in Orlando here, offered up $2,000 for me to hire some undergraduates to scour the internet to find some data sets that were relevant to plate tectonics or spring tides and neap tides, and is there a data set that we might be able to use to get at this content? So in the span of 2 years, we spent $4,000 on undergraduate OPS labor. And yeah, we're hitting, probably by the end of this year, 20,000 students. And I think that's a decent return on investment. And I'm hoping that this will eventually help others figure out how do we embed this into the curriculum that we're already using. Even beyond specific data science courses, but for your high school or undergraduate or graduate level chemistry or physics or anything where you have data that you're analyzing, this has been a really easy on-ramp to provide a working script in Python or whatever that gets students working with this stuff, right? And the next thing you know, they start Googling, right? Well, what are the different parameters for, or arguments for this pandas function or numpy or scipy function that's being called here, right? How do I modify that? Anyway, so I'll wrap it up there and open it up for anybody who has any questions or comments. I'd love to hear what you're thinking, or if that gives anybody ideas of where I and my colleagues should be looking next, maybe. Anyway, thank you so much for having me. Thank you for carving time out of a crazy week that I think we had hoped would be a respite from 2020, and it's turning out not quite yet. So thanks for being here, everybody. And Yeah, and Renata, thank you as well.
Thank you. No, always, always interesting. We had this discussion before, and I have some particular things. But does anybody have any questions for either Mandy or Adam, or just or suggestions, or anything that popped up to you from what they've said so far?
There are a few questions in the chat, in the Etherpad as well.
Okay.
Mandy, I'll respond to your comment. Thanks for the props. And there are great data sets, yeah, for municipal utilities and wastewater and water usage. And we actually have a couple of these activities in the pipeline from my fair state of Florida has lots of wonderful waterways that are ridiculously polluted. But the data is really accessible because we have some state level law that allows public access to most of our institutional data. So we have really bad data, but it's easy to get. And we're hoping that we can work that into some environmental science or analytical chemistry activities as well.
Yeah. So,
thanks, Adam. I was just actually going to comment on, and can I comment, Renata? Or?
Sure, go for it.
I just appreciated the way you went through that first example of how you changed the plot. I think one of the things that's really hard is where to start with people that don't have any background in coding. And we want to jump in with, get our feet totally, get submerged in the water, but you really have to get people's feet wet just with a gradual approach. I really liked that. And so I was just going to thank you for that, because I'm always suffering from a, let's do it all at once. But you really have to back off. And I like that stepwise approach. And I liked that sort of simpler version of a project that you say, okay, here's the data already and carve out something from this. Because when we get data from stakeholders that we then pass on to the undergraduate participants in our research program, they struggle with the structure of the data and how it's put together and how to reframe it in a way that's useful, because oftentimes it's very, very messy, like we were mentioning some of the public data. And so actually even that experience, while very frustrating for data scientists, I think is really important for students to go through that struggle, but it's certainly more of a, not the first thing that you want to experience when you start working on a data science project. You want to have a little bit easier entry. So I appreciated that.
Yeah,
cool. Yeah, I'm a fan of this. Right, sometimes we call that scaffolding, right, pedagogically, to make sure that we have lots of small steps, and that our more advanced students and teachers that use this, they move through those steps really quickly, but they're at least there for the other ones who are just having some major, mental block on what is going on. But yeah, I've been really surprised at how easy that's been to implement.
I love that as well. I would say, there's a question in the chat too, and there was a question on Etherpad about how do you recruit students and teachers to participate in your program?
Yeah, so Renata was kind enough to speak with one group over this past summer of ours. So I do work with a handful of different teacher groups. One is called QuarkNet, which is a US particle physics outreach group. So there we've embedded these activities in teacher workshops that we usually, we used to do Excel analysis on kind of large Excel files. And now we can do ridiculously large data sets with Python. So finding people that are already doing teacher workshops is a great way to do that, right? Because then we didn't need to establish that, the other 95% of the program, right? We're just coming in and saying, hey, here's another cool way to do things. We got school districts to partner with us. Again, like I said, they already have pressure to how do we do more coding and computer science? Our state legislators have told us that we have to do this. They don't know what it looks like and they don't know how to make it happen. Nobody's telling us how to make it happen. And so we found schools and school districts and teachers really receptive. We coupled that with, like I said, with a budget of my position already being funded so that I could help coordinate some of this. A couple $1,000s a year for undergraduate labor to do Google searches for 20 hours a piece. And then the school districts had plenty of budget to pay their teachers stipends to do a summer workshop to get trained on this. Because they were gonna, most school districts are gonna pay their teachers over the summer for a little bit to do training on whatever the flavor of the week is anyway, right? We actually jump in and say, hey, here's something that's free, it's lasting, and we'll help you do it. And so we didn't have to come up with the teacher stipends, which is usually a big deal. You know, a teacher stipend of maybe $100 or $150 a day for 2 to 5 days of training on this stuff, times 200 teachers. Now you start getting into, you know, NSF requests, right? And not just a casual little thing. But school districts are already paying to train their teachers on stuff. So that turned out to be a really nice partnership. I'll jump down to the last question in the Etherpad, which was the real motivator for me to do this is equity and access for tech literacy like this is usually pretty bad. Because for a student to get exposed to programming or data science or advanced science, they either need to have enough freedom in their high school schedule to take that elective course. But if you're also forced to take that remedial reading class, you're not getting to see this. Or it's a after school club, which if you ride the bus, good luck, you're not doing the after school club. Right? Or if it's the thing that happens over the summer or on the weekends, well, you know, if mom and dad or grandma can't drive you to that thing, you don't get to do that either. So our approach was being able to saturate an entire grade level of, you know, Orange County Schools is like the 8th or 9th largest school district in the US. And they just put it into their standard 6th, 7th, and 8th grade curriculum. And so it's not really deep, but we're touching, you know, 80 or 90% of the students in a very diverse school district. I'm confident that if we ever looked really closely at the demographic interactions, we must be connecting with like orders of magnitude more minoritized students than almost any project that I can think of. And that helps connect them with what comes next, right? Now they can come to university and, you know, I mean, even in our engineering and physics majors, right, a fraction of a % have ever programmed before, right? And these middle schoolers after 6th grade are already, you know, ready to run circles around our undergrads and graduate students. So.
Nice.
I'll add to that, Adam. I know that the computer science faculty in our department have some similar outreaches to the K through 12, and their perspective is that the K through 12 can't even hire computer science faculty because they have so many job opportunities. It's hard to hire faculty at the university level in computer science because computer scientists have so many job opportunities. So take that down to K through 12, it's even harder. And so I think that what you're doing is probably filling a lot of gaps for both the students and the teachers.
And we've done this, you know, we've talked through it. So the Jupyter Hub idea, we've thought about that for the universities. The South Hub, we have tried to create with the Jupyter creators a Jupyter Hub that could be run at multi-institutions. So we did pilot that out for institutions that were in our Data Up program. So about 8 or 9 institutions being able to run their own Jupyter, or we run the Jupyter Hub, but they were able to access it directly. I think that our partnership was with Microsoft Azure specifically to do the cloud hosting. And again, that problem of hiring. So we hired a software engineer that was running it and deploying it, even in the University of Puerto Rico, which is part of our South Virgin Islands and other places. But the Google collaboratory thing is something that would be interesting because as you say, with the partnership with the cloud providers, it was a pilot partnership, and then how you sustain it through when people are using it. And at a university level, people start to use it for more research grade purposes. So I'm wondering, you know, at middle school, it's pretty, it may stay under limits, you know, with the cloud limits, but if, you know, expanding it to university partners, you can easily see how one partner could, you know, start doing real research questions in a cloud environment and how that works. So do you have any limits? This is kind of the last question on is it not needed to be limited because of the population you're dealing with, or do you have to install any kind of limits through Google?
No, I mean, Google Colab is not something that, I mean, it has its own sort of built-in limits, right? And I think that you can pay to upgrade, but, you know, we haven't really run into any issues, you know, noticing scripts taking particularly long to run, right? Or running out of resources. So yeah, I've spent a decent amount of time managing Jupyter Hub installs on, you know, AWS and Google Cloud Compute, and just wow, when Google Colab came out, I mean, you know, yeah, that's expensive, right? You need somebody who's dedicated a decent percentage of their time to manage that. With Google Colab, there's zero upkeep. The downside is, you know, you're holding hands with Google and your users need a Google account. That's not such a huge ask, I think, initially. But the 2i2c.org, I think that's maybe the next great hope on what a next solution might look like for that. That's maybe a bit more cost effective. Yeah, I think
so
Donald,
they're partners with us as well. I think 2i2c, they're a partner on a new project. So we are looking at that, but it was just interesting in the timing on it,
yeah.
of how that works. So I love the Google Collaboratory. It's always been good. So thank you again.
Last comment is, Donald, I noticed that you mentioned in your intro on the Etherpad that maybe it would be nice to see us coalesce on some set of standards for stuff. And I know that everybody who suggests that is going to suggest their own standard. And so now we go from 10 options to suggesting another one, and now we have 11 instead of condensing to one. But I think that not necessarily Colab, but I think Jupyter is worth looking at because it natively handles Python, R, and Julia. And I think that's a decent suite, as well as handling the whole SciPy stack really nicely on the Python end. I haven't used it for R, but I know a bunch of folks who do. So that might be worth, yeah, that might be worth a conversation, or at least being in that discussion. Also because of Google Colab being able to support that. Now you have a free, you know, easy thing to implement for, but you know, school districts don't have a budget for somebody to manage their Jupyter Hub. And we went through that for about a year, and we found another for-profit company that was going to do a Canvas plug-in to run a Jupyter Hub through their students' Canvas learning management account. And yeah, we wrestled for a long time, and then Colab came up, and it was just like hitting the easy button.
Yeah. So yeah, that's something we should definitely talk about. If others are interested in that, put that in the pad for sure, because I know we're interested in that, you know, trying to make that case for at the undergraduate level. I think it's very similar around on-ramps and even sharing curriculum or sharing data sets. Jupyter may also be a good thing to look at, as you say, as a way for some of these projects like what Mandy was talking about and others where you have resources already in R or Python or Julia. But most things have been in R and Python, and having a way to put that together. Also looking at the Jupyter books, that's something that is new or something I hadn't heard of before, because we called our Jupyter Hub interactive textbooks, like that we were trying to help people do interactive textbooks. So that's an interesting thing as well. All right, well, it's after time. People, we can stay, but anyone who needs to go, feel free. We will have a forum if this is something that's interested in what you're doing. Again, love to hear it. Thanks, John, for coming. If you have a few minutes, Adam or Mandy, if you see questions in the Etherpad, you could answer those, or reach out to those people. That would be good. We leave these live till the end of the day. So if you also think of something after we've all gone, which always happens, and for anyone in the group, and you say, hey, I should have said that, or I should have put it in there, you can put it in there, and we will still keep them and look at them. All right. Well,
I'm free to hang out for a few minutes if anybody wants to chat about anything, and I'll also respond to some stuff on the Etherpad.